Hi and welcome to Group's 7 CDR presentation. The purpose of this video is to explain the project's main idea and to explain how it has been evolving since it started in Senior Design 1. We will also show our work's current state, some functionality demos that we did for sensors and parts of the project, and the projection of development to satisfactory conclusion for the product at the end of the term. Our primary motivation was to develop a comprehensive tool that could be used by scientists as a source of reliable data to perform research about the lakes in Florida. The data was thought to be a set of arrays that would be populated by sensor inputs, for example, pH sensor, temperature sensor, and other sensors, for example, gases sensor, among others. By consulting literature and primary sources, the team agreed to redefine the project's purpose to be a design of low-cost devices that are precise enough to determine important lake parameters that will help the user to figure out if the government's assistance is needed at the lake where it is being used. The problem of dangerous cyanobacteria and algae blooms are two of the most common but important problems to do research about in lakes. There are some signs, for example, some changes in pH or the presence of certain chemicals or gases could be assigned to predict the production of algae or bacteria. This is a tool to provide a warning for lake owners when there are conditions in their lakes that deserves to be considered and maybe request a lake treatment.
Moving on to the actual cost and budget. As of today, we have spent around $600 for our parts. This amount is lower than the budget we set out to be a maximum of $1,000. Unexpected expenses had to be considered, as they often happen because of something like a broken part or a part that just simply does not work correctly. We estimate that with unexpected expenses, we will spend a total of $800, meaning $200 more than our current cost, which would still be under our predetermined limit of $1,000. Let's talk about our goals. During our reflection on the goals we wish to achieve with this project during our Senior Design 1 class, we came up with the following goals. Build a project that assists in monitoring, researching, and understanding the lakes around us. The project will contain sensors that collect data regarding air and water. The data collected should be stored in a place like on a cloud and accessed for review at any given time. Collected data regarding those lakes will be valuable parameters in assisting lake studies. Have a functioning device that floats, and it will be moved using a remote control. It will also contain solar panels to use the sun to help keep it running. Some discussions helped shape our goals. We had discussions with experts on the field, like with a biologist, Julie Bortles, who works at Orange County government, that helped us get a better idea and understanding of what is already present to them, what their needs are, and what could be something that should be improved in their current technology. One of the biggest takeaways was that with their current technology, they do not do as many readings as wanted because of how much it would cost them. In other words, it was a budget issue. With that in mind, we thought about how we could bring something that helps the mentioned issue, and we added another goal, which is creating a low-cost project that could provide multiple readings to help the need of experts in that field, like discussed with a biologist. All the previous mentioned goals remain valid even after the discussions we had. We had three main objectives we defined. The project needs to be completed in the allowed time frame, meaning the 150 pages document had to be completed during the spring 2023 semester, and the project has to be fully built and done during the summer 2023 semester. Another objective is that it has to be fully functional, meaning all described features have to be implemented and working during the summer 2023 semester. The last objective is that the material cost should not exceed $1,000. As our goal is to provide a low-cost solution, keeping a budget of $1,000 is reasonable. When it comes to the material cost, it will be equally divided among team members since the project is not sponsored by anyone.
Requirement specifications. Our system has been carefully developed to meet specific requirements, and during this presentation we will focus on three key features that will be demonstrated: pH measurement, bug collection, and remote-controlled movement. Firstly, our system is equipped with a highly accurate pH sensor capable of measuring the pH level of water. With regular measurements conducted every hour, we obtain valuable data regarding the water acidity or alkalinity. This information is crucial for various applications such as water quality assessment, aquatic ecosystem monitoring, and industrial processor. Our demonstration will showcase the system's ability to provide real-time pH reading, allowing us to monitor and assess the water's chemical balance effectively. Moving on to the second feature, our system also includes a bug collection mechanism. Bug being indicators of environmental health can provide valuable insights into ecosystem. By collecting bugs from the water, we can monitor and analyze their presence and diversity, aiding in the environmental impact assessment and identifying potential risks. The demonstration will highlight our system's ability to collect bugs efficiently with a minimum collection time of 1 minute. Witness how our technology contributes to understanding and preserving the delicate balance of aquatic ecosystem. Our system is designed for convenience and flexibility. With a remote controller, user can easily move the system to desired location within Intel lakes. This feature allows for quick and efficient data collection from multiple points of interest, enhancing the system versatility in various monitoring scenarios. During the demonstration, we will showcase the system's smooth and responsive movement, all achieved with a response time of fewer than 2 seconds.
We used the House of Quality to visualize the design aspects and the requirements for our project from two important perspectives, from the engineering perspective and the customers using the product. Customers' requirements are a list of the aspects customers would like to see in our project. The requirements includes a low overall price, making the product easy to use and easy to take care of, so that they can maintain the product for as long as possible. To improve the customer satisfaction even further, it is important that our product is durable, so it can survive and withstand hot temperatures and heavy possible rain in the area. Meeting these requirements would result in a greater satisfaction from the customer end after using the product. The other part of the house of quality diagram is the perspective of engineers designing the product. For our project, we decided to focus on mitigating the size of parts to make the overall form factor small, in addition to the design aspects of making the product lightweight. Also, we are trying to maximize the reliability of the power, which includes the use of a battery and solar panel. Furthermore, in order to provide a reliable data for the user of this product, we are attempting to maximize the data throughput of the system. The two last features in the house of quality diagram focuses on features in the system to be able to maneuver and collect samples on the water from the water.
Let's now talk about our hardware block diagram. As you can see, our project has a lot of moving parts that we plan on achieving. And starting at the top of our diagram, we plan on connecting solar panels to power our lab toolkit. Our solar panels will recharge our rechargeable batteries, which will then be connected to our power supply, which will power our system. Our power supply will be connected to our PCB, Arduino, and our sensors. Since our project consists of water and electronics, we need to make sure that everything is securely waterproof, with only our sensor extremities being exposed so they can collect the data that we need, and everything else being safely stored in the waterproof container. Also, we will have an RC boat pulling our system, making it so it is maneuverable in the water, allowing retrieval and deployment in central parts of the lakes. Our bug collection device and water collection device will be attached to our system externally as well. With our hardware system being completed, we will then need to send this information to our database.
Moving on to the hardware comparison and selection of our project brain. Multiple different technologies can exist and be used as the brain of our project. For example, there are microcontrollers like TIs or Arduinos that widely exist on the market. Some advantages are that they are already fully functional at purchase time, they have libraries available to them, and they allow fast prototyping. A disadvantage is that they can have limited processing power. Another technology is designing PCBs. An advantage is it allows flexibility because of the custom design we do. A disadvantage is that it could take a while to have a fully functional designed product, since the product might go through multiple iterations before getting the wanted result. Let's explore the chosen technology for the project brain, which is the microcontroller. In Senior Design 1, we did not know that development boards would not be allowed, so we chose the microcontroller after comparing technologies. We had chosen the Arduino Uno Wi-Fi Ref 2 because of its Wi-Fi and Bluetooth capabilities, the availability of libraries with it, and the ease of use, which made it stand out compared to other boards that did not have features like Wi-Fi built in them. When it comes to recharging the power supplies, which is batteries, we will look into two technologies available. The first is to manually take out the batteries from the project and charge them using a charger, then putting them back inside when fully charged. An advantage of that technology is that it does not depend on the weather to charge the power supply. A disadvantage would be inconvenience since the product has to be taken out of the water each time the battery dies. The next technology is using solar panels. Some advantages are that the product stays in the water, which is a huge convenience for users since they do not need to manually do something to charge the battery. And it uses a renewable energy source. A disadvantage is that it is weather dependent, meaning some days without the sun might not be optimal to charge the batteries. Let's talk about the chosen technology to charge our power supply, which is solar panels. After comparing multiple solar panels on the market, we ended up choosing the semi-flexible monocrystalline. This model offered a power of 5 watts, while the others only offered 1 watt. Another factor is its weight. It was the lightest weight of the researched options, which is an important factor when it comes to a floating device that will remain on the water. The working temperature was also among the best of the options researched, meaning it can work in weathers that are both very hot and very cold.
Air quality is an important parameter to consider in leg research. Choosing the best option is key for producing reliable data that can be stored and used. Adafruit SGP30 sensor was selected not only because the price is competitive with respect to other options for its reliability, the wide range of projects that are currently using it, which translate in robust community support. It has been tested and debugged many times. It also counts with low power mode features and is native to Arduino, which makes it more attractive for our project. Even though we did not consider the MQ135 as our second option during Senior Design 1, after testing different hardware empirically, we found that it could be an excellent option as well. It worked out properly, but still good enough to provide reliable data.
Container comparison. For our floating lab project, we carefully selected the Uno R3 case as the ideal enclosure for our Arduino Uno R3 board. This choice was driven by several key factors. Firstly, the Uno R3 case offers compatibility, providing a secure fit and protecting our board from damage. Secondly, it ensures robust protection against water, dust, and impacts crucial for challenging environmental conditions our project will face. Thirdly, the case grants easy accessibility, allowing convenient connectivity and customization with cutouts for additional sensor or models. Moreover, its compact and lightweight design ensures portability and maneuverability in remote locations. With the Uno R3 case, we can confidently deploy our floating lab toolkit, gather precise environmental data, and conduct our research effectively. Water temperature sensor. The DS18B20 temperature sensor is among the greatest water temperature sensors compatible with the Arduino. It is a very precise digital temperature sensor that works with the most microcontrollers and electronic devices because to its wide working voltage range. Also because of its waterproofness, it may be used in submerged areas. The one-wire protocol of the DS18B20 temperature sensor makes it simple to link it with the Arduino Uno Wi-Fi Level 2 and include it in our project.
Choosing the best power supply battery for our needs is crucial to get the desired outcome in our project. There are many types of batteries that we considered to use in the project, such as lithium-ion, nickel metal hydride, and lead acid. We have chosen the power source based on the reliability of the battery and its performance in our project. Knowing that boards typically operate at 5 volts, we needed to consider the voltage of the battery and how it can operate. Also, the capacity of the battery plays an important role in determining how long it can power our boards. Having a rechargeable battery for our project is essential because of its cost effectiveness in the long run and its compatibility for our solar panels. Since our project is aimed to be used in lakes and areas where the environment could be affected greatly, choosing the source of power that minimizes the amount of harm it does to the environment is necessary to consider. By considering all these factors, we chose the best option that meets the requirements for the project's power requirements, safety considerations, and budget, which was the nickel metal hydride from TNF.
When looking for pH sensors, we had three things in mind: reliability, price, and accuracy. This led to us finding two options: the gravity analog pH sensor and the AnyLeaf. We first had to make sure that both our sensors of choice would be compatible with an Arduino and a PCB, which they both are by using I2C protocol. Next, we had to see what range of pH they could read and how accurate the results would be. And when comparing the two options, they both could achieve the same range of pH of 0 to 14, where the AnyLeaf had an error of 0.01 compared to 0.2 of the gravity sensor. The form factor and weight were practically the same for both, but the response time for the gravity sensor could have up to a 2-minute delay when reading, which is not advantageous for our project because of the complexity of having multiple sensors, while the AnyLeaf did not state this problem. And lastly, the price, where the gravity sensor was $30 cheaper than the AnyLeaf. We ultimately decided to select the AnyLeaf, even though it was more expensive. This was because of the reliability in data collection and the extreme difference in accuracy. As one of our design requirements is pH reading, we decided to put an emphasis on this aspect. Next, data transmission. An important part of our project is sending data from the system to our database, and we looked into 4 different ways of transmitting our sensor data. At first, we thought about using radio frequency to locally transmit our data, but since we wanted our project to be flexible by location, we decided to stay away from this form of communication. Next, we compared the difference between cellular and Wi-Fi transmission, where depending on what we chose, the frequency range would be different. We first eliminated the SIM 900A because 3G was no longer supported in the United States and the input voltage was higher than desired, which left us with the ESP8266 Wi-Fi module and the SparkFun LTE Shield, where both would allow us to transmit our sensor data. We decided to select the ESP8266 Wi-Fi module because it is already included in our selected Arduino, which would make it more affordable to use the technology that we already have in our system instead of adding an expensive alternative.
Before we even thought about the PCB design, we defined the specific functionalities and types of data that we needed to have. The PCB has to integrate at least the pH sensor, temperature sensor, and gas sensors with a SIM card module that will serve as a bridge of communication between the hotspot and the device, and then to send the arrays of gathered information to the cloud. Since the summer term is significantly shorter, one of the biggest challenges is the time constraint in between the cycles of design iteration process. The PCB design iteration process consists on performing significant PCB design, then revise the design, send the Gerber file to the manufacturer, then wait the delay in shipping to receive the PCB, test the PCB according to expectations, debug the PCB, correct the design, and the cycle repeats. This process of iteration takes time, and it is a big challenge when the deadlines are short. The PCB is still under final development process, and it will be explained in great detail in our final video.
Now I will talk about server selection and hosting. For our project, we initially looked at using 3 different commonly used stacks, these being LAMP, MERN, and MEAN. We decided to narrow it down to MERN and MEAN because of the use of JavaScript and MongoDB. This is because our team had more experience using JavaScript than PHP and a preference for MongoDB over MySQL because of MongoDB's Atlas, which is a cloud database. And then we were left with choosing either React or Angular for our front end, where we decided to use React because of our prior knowledge and it having more community support in the development community. With hosting a web application, we looked into 3 solutions that could host our stack. First, looking at having a local hosted instance which we initially ruled out because we decided not to use RF transmitters. Next, we looked at using a DigitalOcean droplet or an Amazon EC2 instance, where both are virtual machines that are hosted in the cloud, which would allow for our stack to run. With both having the same capabilities, we decided again to go on familiarity, where our group had prior experience using DigitalOcean. Ultimately, we ended up making changes already, and we decided to switch from Express.js and Node.js to Next.js, which is a variant of Node.js, but different, where Next.js integrates better with React and is better for server-side rendering, which is important for our project, where we are updating sensor information constantly. As well, it is easier to write API endpoints using Next.js because of the page structure it uses. Also, we decided to do this because of the easy integration with GitHub for deployment and their service for Cell, which makes the deployment easier because all you need is a GitHub repository and an account. And lastly, we switched from using Bootstrap to Tailwind because it's directly supported with Next.js. Next, our software design for our database. For our application, we attempted on making our project future-proof, and this started with our database, where our database uses MongoDB Atlas and consists of one database with two collections, where one collection stores all the sensor data from our lab toolkit with a timestamp and a unique toolkit identifier. Now, let's talk about our software block diagram. As soon as our lab toolkit is turned on, it will start recording and sending our sensor data to our database. We will combine all the sensors input into one array, which will then be converted to JSON, so it can be sent to our database. We will use HTTP post request to send our data by using the MongoDB API. This will allow us to write to our database. Our design for our web server will consist of two pages, which Next.js will allow by linking pages together. Next, you can see how the user will interact with our web server, where they will be prompted to make an account, and then they will have access to their lab toolkit data on the next page. The second page will be a table of all the sensor data provided from the database, where the user can then search for data points.
The idea is to define a data type for the project that will be sent as a package that contains all what is measured by the lab tool in the lake and that is essential to understand the lake's health. A red flag will be raised when empirical measurements for parameters are above or below the expected values. For example, if pH is below the threshold, it will be noticed and reflected on the data pack sent. One of the important ideas in this project is to identify the essential parameter that worth to be standardized and to create a data type that could be easily analyzed and that could optimize lake analysis and diagnosis.
For the work distribution, our group consists of 3 electrical engineers as well as 2 computer engineers. The end result of the project should be capable of meeting the requirements we agreed on. In order to utilize our skills in the most optimal way, the work distribution for our project is shown in the slide. The roles in the project were chosen based on each student's specialization, interests, and strengths.
Progress, Senior Design 2 Project Milestone. Now, I would like to provide you with a brief overview of our progress and milestone for our Senior Design 2 project. Our project is structured according to a timeline that encompasses the entire summer semester, and I will highlight the key milestones achieved in each month. In May, our focus was on building and testing the components of our project. We dedicated our efforts to assembling the necessary hardware and conducting thorough tests to ensure their functionality. This phase laid the foundation for the project's success. Moving on to June, we shifted our attention to software development. We worked diligently to create software progress and applications that complemented our hardware components. This involved tasks such as programming interfaces and implementing algorithms enabling our system to operate smoothly. As July arrived, we delved into testing, final paper preparation, and crafting our presentation. Rigorous testing ensured that our integrated system functioned reliably. Simultaneously, we dedicated time to documenting our project in a final paper, capturing the entire journey from inception to result. We also prepared a comprehensive presentation to showcase our achievement and insights.